This video deals with working with data. It's part of the modules associated with making meaning out of the observations that you've had from the instrumentation. The very first thing you have to do and realize the general idea is turn the raw data into information. So you have to get it in a usable form, understand the patterns that are there, delimit whatever the patterns are, interpret those, then quantify them, and check for errors along the way. Usually the raw data is just a column of numbers in a file. This shows them in Excel. It's just one piece of one number after another organized in time. So the very first thing to do is to plot the stuff and then look for patterns. There are three typical kinds of patterns: peaks, shifts in value, and some sort of waveform information. For chromatography and many other areas, peaks are the kind of data that you'll look for. Those are the patterns. And so what you want to do is work with them this way. You plot the data, look for the zero line, set it up so it's zero is correct. That way you can adjust the scale without the peaks jumping all over the place. Then replot the data, but take away any plotting regime that puts lines in between the data points, just to make sure there's enough data points there to get a reasonable representation of the phenomena. One thing you can do if you hunt for all the information is add the derivative and co-plot it to the raw data, as you see the green line here. This lets you find little smaller peaks that you might miss just looking for them. These patterns that go down, up through zero, up, and then come back down have very characteristic points which you can understand from your calculus. The maximum value downward is at the center point of the slope of the peak, so it's the midway, it's the inflection point. When it comes back up and crosses zero, at that place where it crosses zero is the peak maximum. And then similarly on the way down the other side of the peak, you find the inflection point of the slope and so forth. So we've adjusted slope and we've adjusted scale a little bit. Now let's blow up the peak and look for any funny things that are going on. It looks well behaved here, but when you replot it, you'll notice there's a baseline slope and some peculiar artifact on the far side of the peak that you didn't see. That sometimes is caused by chromatography, or by pressure effects in GC, or by a detector that's not properly engineered. So look at the front edge of the peak, the baseline before it. There's nothing special there that you can do. You might want to put a straight line through it if you want to spend some time. And on the far side of the peak, there's nothing much you can do there. So why did we do it? Well, we did it so I can identify the peak start and the peak stop. And as you can see on the left side, peak start, depending on your assumptions, no drift, or a constant drift, or drift only from peak start, gives you different places to call what peak start is. Similarly, over on peak end, you have worse problems. You have to decide what you want to find for peak end, and it has various assumptions. These become clear when you do quantitation of the peak by the two different methods that I'm going to talk about next. These two methods are the peak height method and the peak area method. The peak height method is really straightforward. It's really the distance, the height, or the voltage difference between the value at the very peak maximum and the imputed or expected or pretended to know baseline value underneath the peak. You do it by finding the max, find out where it is in time or whatever variable you have, and then go figure out what you want to use for a baseline, drop the vertical, and you're there. The integration is pretty simple. You do the same thing. Peak start, peak stop, and you're done.